start lecture 26. And topic, we will continue our discussion on passivity, and today we will try to connect it to mixed potential theory. Fine. If we try to see the discussion what we had in our last lecture, this is the diagram what we have drawn. So, if we try to see only the now we have seen that this zone is passive zone. Now, after that either we can have increase in current density due to transpassivity, or due to oxygen evolution reaction, or due to formation of porous film, or due to breakdown of passive film, due to the effect of chloride ions or halides. So, now if we try to pinpoint those points, those particular, let us say if we start with transpassivity, when we have transpassivity, the line starts moving towards right again, and we have seen those zones. This is active zone, this is E equilibrium of metal, and this is I 0 m over m surface. This is I critical, and corresponding potential is EPP. We have ECP, which is complete polarization. Then we have E trans. Okay. So, this is transpassive region. So, this particular region we call it transpassive, and this particular thing can also appear due to even if the transpassive, that means the metal oxide does not get affected or it does not get broken down, there could be anodic plot like this, increase in current density, that could appear due to oxygen evolution, but we are not talking about oxygen evolution anymore. Assuming that this polarization line is not making a it is not crossing the oxygen evolution line. So, if it happens like this, we have talked that metal forms some complex metal ions which will not have any protection ability, rather it would try to dissolve. For example, one such example is chromium. Now, chromium trivalent ion, which is nothing but Cr2O3, which gives a protection in case of chromium, but if it goes to a high potential. So, in case of chromium, the chromium passivation appears because of chromium oxide formation. Now, the trivalent chromium ion can react with H2O and then form Cr2O7 minus 2 plus 14H plus 6E. This reaction can happen, where this is the transition it can have, where this one can dissolve. So, the oxide layer will no more be passive, rather it will start dissolving. So, this we are talking about, this we are indicating as a transpassive zone. Now, this is one instance. So, this is case 1, where transpassive relates to formation of complex metal ion which allows the oxide passive layer to dissolve. Fine. So, this is case 1, and then you can have increase in dissolution again, IA would further increase. And then there could be another situation which appears case 2, this is case 1 and this is case 2. Let us say in case of aluminum, if we increase the potential further, then we can have, if we increase the potential further, the plot can be like, let me pinpoint those points, this is A, B, C, D, E. I am not using E because E is expressed as potential. So, I can mention as F, then this is G, H. So, if I go in case of aluminum or titanium, if I go further positive potential, if we take forcefully that metal to a positive polarization, if we allow that positive polarization, anodic polarization to take place. So, the polarization line can go A, B, C, D, G and H, and a higher polar since I am increasing the potential, my layer thickness, this is the metal surface, let us say, and this is the layer that is forming, passive layer, this is passive, this layer is forming. Now, as we are increasing the potential, in order to maintain the constant electric field, the thickness has to increase, and when it increases, there could be possibility of formation of a porous layer on top of this adherent layer. So, this is a porous layer that can form. Okay. So, this porous layer, when it forms, we call it anodization. Okay. So, this anodization, or we call it anodizing or anodization. So, this anodization is related to some of the metals like titanium and aluminum. Since it is a porous layer, the dissolution rate further increases, and this thickness of the porous layer could reach up to 200 to 300 micrometer. Since it has to increase, the thickness has to increase. So, that is what this porous layer forms. This is anodization. Okay. Now, again, if I consider case 3, there could be a possibility of case 3, if the solution has chlorine, bromine or chloride, bromide or iodide, these are the halides. If we have halides in the solution, then there could be breakdown of the passive layer, and it happens early, very early in the process. So, like here we can have a breakdown like this at this point. So, this is, we can write is at E breakdown, generally it is written in a small form EB, and this is breakdown. So, this breakdown happens because of this reaction, this metal, it can react with chloride, which form metal chloride plus 2E. So, again we could see that it is a basically anodic process, and that is what the reaction again goes towards anodic side, and because of this the anodic, this metal oxide layer dissolves, and this dissolutions happens mostly localized dissolution. Which lead to PT. Fine. So, this is another process that can happen. Okay. So, if this particular segment I can have a very for example, if this is E, this is log I, the plot could be like this. I can have this, and I am talking about breakdown part, then it can have like this, or it can have like this. Now, I could see that if I compare these three cases, this is A, B, C, I can say that passivation attainment, if I try to compare, C has got lowest passivation tendency. Why? Because its I critical, of C is greater than I critical of B, greater than I critical of A. Now, how does it make sense? Because higher the I critical, lower would be the formation of metal oxide layer on the surface, and that would also reduce the tendency for the coverage of the metal oxide coverage of the metal surface. So, we will not come across that situation where the retardation of metal dissolution would be equal to the acceleration of metal dissolution, and this retardation of metal dissolution, as we have discussed, it happens because of the coverage of metal surface by metal oxide. So, we need to go a very high current density, and by that time it starts forming metal oxide because of the very rapid dissolution, because I critical is nothing but the IA. So, that means a very rapid dissolution takes place, and there could be a surface perforation even because of the rapid dissolution. So, we lose out the passivation. Now, coming to the other segment, if we try to see this breadth, passive region breadth, there also A has got higher passive range, as well as it has, or I would say highest among all three A, B, C, lowest I passive, that means passivity, passive current density. Okay. So, it also indicates that it has A would passivate quickly in comparison to if we comparison to B or C, and of course, B has a little better than C. So, that means we could see that higher I critical is not good. At the same time, wider passive region is good, but we have to also see that wider passive region should accompany a lower I passive. So, then we can say that that metal has got a very good passivation tendency. Now, if we try to see the breakdown, we could see that if this is the EB, so this is EB for A, this is EB for B, and this is, so this is EB for C, and we could see that EBC is lower than EBB is lower than EBA. So, this also indicates that breakdown of passive film is most prominent in C. So, the critical aspects, if we consider, we have to look at EP, ECP, IP and I critical. So, these three are very critical critical parameters for attainment of passivation. Now, interestingly, we have been talking about these three quantities, but we have not yet discussed one important part, which is this segment. So, which is basically the zone between EPP and ECP. So, we have to talk about ECP and EPP. This zone, this is a range of potential where I could experience a growth of metal oxide and complete coverage of the metal surface, and then finally we will achieve to that situation where rate of oxide growth is just exactly equal to the rate of dissolution. Now, here if I try to see, in order to understand the importance of this particular point and this particular point and the relative position, we have to introduce mixed potential theory. Now, even without having a knowledge of mixed potential theory and the interaction of passivity and mixed potential theory, so we could see that in this case, in case of A, this gap is minimum. Here the gap, as we are going from A to B, I could see that the gap is increasing, and in case of C, it is the maximum, this gap is increasing. Now, what does it mean? That in order to get to the passive region, that means in order to attain that IP, I have to go to a much higher polarization before we could achieve that passivity. Now, why this breakdown is happening at an earlier state? For example, if we try to compare a kind of situation like this, this is one, this is second, this is third in a same metal, I could experience this kind of situation where chlorine ion concentration increases, EB decreases. So, that means the breakdown potential reduces. So, there could be influence of increase in chlorine ion because, and that could lead to decrease in breakdown potential, or there could be inherent tendency of that metal oxide over that metal, which could have a lower affinity to chloride or higher affinity to chloride. If it is having higher affinity to chloride, then it would immediately react with chloride ion and then dissolve into the solution, and that would lead to the breakdown of the passive film and lead to pitting. So, now This gap is also another important factor. So, which is ECP minus EPP. So, this potential gap, this is also critical parameter. Now, when we talk about the influence of when we combine this passivation along with when we combine passivation with the mixed potential theory, we would realize the importance of this ECP and this EPP, this gap. So, in order to do that, let us get to a simplistic situation, like if we consider two situations, this is E volt, this is log I, this is log I, this is E volt. Now, if the anodic polarization plot looks like this, and let us say we are not talking about oxygen evolution, rather we are talking about transpassive region. So, this is transpassive and this is passive and this is active, and this zone I can term it as unstable zone. Why this is unstable zone? This gap between EPP and ECP. This in this gap, the system hasn't attained the steady state yet, because we have talked about steady state in this zone and the metal hasn't achieved that steady state. So, in this zone is a basically unstable zone. If there is any disturbance in between, the system can go back to this, or if we continue, if there is no disturbance, the system go towards this. So, I will talk about this disturbance, what do we mean by this disturbance, but at least one thing is appreciated here, that we are trying to reach the steady state which is corresponding to IP. Now, if hydrogen evolution reaction interacts with this particular, let me put this hydrogen evolution reaction in the form of red color. So, this is the hydrogen evolution reaction which is IC hydrogen on metal surface. So, this is I 0 of metal on metal, and this is I 0 hydrogen on metal surface. This corresponds to E equilibrium hydrogen, and this is corresponding to E equilibrium of metal. Now, when we have this, now as we have understood last time when we talked about how do we get the experimental plot, let us say this is log I and this potential, we have this two lines are intersecting, this is IC hydrogen, this is IE of metal. So, we always divide, in this case this is E core and in this case E core is this one, and here it is E core, and if we take polarization below E core, so our plot nature would be like this, where this indicates I applied equal to IA minus IC, and this indicates I applied equal to IC minus IA, because in this case IC is more than IA and in this case IA is more than IC. The same difference kind of this, we have to take difference between these two currents. If we take difference, our graph pattern would look like this in this case. So, this is the E core value, the graph pattern would be like this. Now, as we go higher and higher polarization from this, So, it will be same like this. Now, once it reaches to this, so from there the current density further goes down. So, it will follow this track, and then since this is in the log scale, so the influence of this current density over this will be absolutely minimum. So, then it will go like this and then move like this. So, what will be the plot nature? The plot nature would be fine. So, we are getting a experimental plot like this, which is basically the interaction of cathodic process and anodic process, and here the cathodic process we have taken hydrogen evolution, and here this is the metal anodic polarization of the metal in the entire passive zone we have considered. So, this is passive, this is active, and this zone is unstable zone. So, how we get the experimental plot, that is also clear, and that happens because of the mixed potential theory. So, the mixed potential theory, as per the mixed potential theory, this is the point which corresponds to E mix, and this is the point where I will have I c equal to I a, and we get this curve. So, when we have this kind of plot, since it is going from active to passive, we call it active passive transition. So, we will talk more on this in our subsequent lectures. Let us stop here. Thank you very much.